4.5 is concavity and points of inflection, and the second derivative test for relative extrema. Before we get started on the book stuff, I wanted to show you a graph. Pull this up here. So here's a graph. It has a tangent line on there. I'm just going to get rid of the tangent line for just a second. I just want you to think about this point for a second. So as this point goes, it's going across here. The slope right now is decreasing. So it's getting closer to 0. As you go down here, it's still decreasing. It's going from 0 to negative. It's getting a little bit steeper in the negative direction. Somewhere in there, the slope starts to get closer to 0 again. So it's actually increasing, until someone in there, and then the slope starts to decrease again. So it's getting closer to 0. So you can kind of see how it just changes. It goes from, the slope goes from increasing to decreasing throughout on different intervals along that graph. If you look at the tangent line as you go across there, so again, somewhere in here, the slope changes, and now the slope is decreasing. When the slope is decreasing, I want you to notice the tangent line is above the graph. Right, it's decreasing. Somewhere in there, it changes back to increasing. And notice where the tangent line is now. When the slope is increasing, it's below the graph. I get up in here, the slope changes now again to decreasing. It's above the graph. Somewhere in here, the slope changes to increasing, and you can see now that it's below the graph. So kind of keep that in mind as we go through and talk about the book. What we're going to focus on is the second derivative. So we know the second derivative is the slope of the slope. It's the rate of change of the slope. So in other words, we're going to say, is the slope increasing or is the slope decreasing? And one way we can tell, again, is where the tangent line is. If the slope is decreasing, the tangent line is above the graph. If the slope is increasing, the tangent line is below the graph. So if you look at now in your book here, right, it talks about a graph with this shape is called concave upward. So if you look at that graph off to the right, if your tangent line is below the graph, it looks like a smiley face. That means it is concave upward. Right? The tangent line lies below the graph. The slopes of the tangent line are increasing, which means the second derivative is greater than or equal to 0. Okay, this second graph has a shape that is called concave down. Right, it looks like a frowny face. And if you look at the tangent line, right, the tangent line is above the graph. Remember when we looked at that graph a second ago, we said if the slope was increasing, then the tangent line was always below. The slope was decreasing, the tangent line was always above. So if you look at that, that means that the second derivative is positive when it's concave up. The second derivative is negative when it's concave down. So here's a little way to remember this, right? Concave up, positive, smiley face. Concave down, negative, frowny face. A point of inflection is when the graph has a tangent line at that point and the graph changes concavity at that point. So if you look at this graph, this is the graph of y equals x cubed. From here to here, the graph is concave down. From that point on, the graph is concave up. Right, so we say that at 0, 0, the graph has a point of inflection. Okay, so the graph has a tangent line at the point, number one, and number two, the graph changes concavity at that point. Some textbooks use other definitions for points of inflections that don't require the tangent line to exist. The AP test, they make sure this isn't an issue. Like they're not going to ask you a question where that comes up. In this textbook, though, we're going to say those two things have to be true. Okay, our definition of a point of inflection is the graph has a tangent line at the point, and it changes concavity at a point. It goes from concave up to concave down, or concave down to concave up. All right, so let's look at this graph. In fact, I want you to do this. Why don't you pause this and go through and answer these 4 questions. You're just looking at the graph and looking at concavity. You decide what you think, and then we'll come back together, and you can share with, and I'll share with you what I think, and we can kind of compare that to what I got. All right, so in which intervals is the graph concave upward? That would be from -2 to -1, right in there. From 1 to 3, right in there, it's concave up. And from 4 to 5. Number 2, what are the intervals when it's concave downward? Well, it's concave down from -1 to 1, right in there, it's concave down. From 5 to 6, right in there. When is there no concavity? Well, that's right here, the graph is straight, so it's not concave up or concave down. Remember, we're looking at how the rate of change of the slope. Well, the slope is constant. It doesn't change. Also right here, slope is constant. It doesn't change. There is no concavity. Where are the points of inflection? So if we use the definition of our book, we would not include this as a point of inflection, only because even though it changes from concave down to there's a change in concavity, the tangent line doesn't exist there because there's a sharp turn. So there would be one at 1, 1, and there'd be another one at 5, 1. All right, so analytically, when we go to find the concavity of intervals, we can do that by looking at the second derivative. So the second derivative is the slope with the slope. It's the rate of change of the slope. And so we can look at if the second derivative is positive or negative. If it's positive, that means the slope is increasing and the graph is concave up. If it's negative, the slope is decreasing, which means it's concave down. So by taking the second derivative and doing the number line, just like we did with the first derivative, remember the first derivative told us relative max or relative mins. The second derivative tells us whether it's concave up or concave down, and we can also use it to find points of inflection. Most textbooks use open intervals for concavity, but there's no universal definition of concavity. So there's some chance of ambiguity. A few texts define concavity in terms where there is a first derivative is increasing, decreasing. So the same issues arise with it, including excluding endpoints. So remember that whole open interval, closed interval. We're going to use open interval. We're not going to include the endpoints. When we talk about concavity, that's the way this textbook does it. But like it says here, there are some textbooks that do include that. So again, this isn't something that's going to come up on the AP test, like we talked about before. They're not going to care if you use open or closed. But again, we're usually going to use open when we find those. Okay, let's go through an actual example. This is determine the points of inflection, discuss the concavity of the graph. Okay, so this is what you have to know, right? Relative max, relative min, that's your first derivative number line test. Concavity, points of inflection, that's always your second derivative number line test. So let's find our second derivative. So let's find our first derivative. That would be 4x cubed plus 3x squared minus 6x. Find your second derivative. That would be 12x squared, 6x minus 6. And now, just like we did with the first derivative, we look at this, but now with the second derivative, we want to find our critical numbers. So to find the critical numbers, we're going to find out when is the first derivative undefined. And if you look at this one, the second derivative is never undefined. That's a polynomial, so we don't have to worry about that. The second thing is, so we're going to put this down. Second derivative is never undefined. The second thing we want to find out is when the second derivative is equal to 0. So let's figure that out. So I'm going to set the second derivative equal to 0. Let's see, we can divide everything by 6. Now I'm going to factor that. 2x and x, it's got to be minus 1 plus 1. Just have to make sure you put the minus 1 in the right spot. I think it goes this way. Let's check that. Let's say that'd be 2x times 1. 2x times 1 is 2x. Minus 1x gives me a plus x. So that would be the right factored form. Set each of those equal to 0. So we're going to go, let's see, 2x minus 1 equals 0. So x equals a half. X plus 1 equals 0. So those are my critical numbers, okay, at a half and negative 1. Okay, now we're going to put on a number line. And up here I'm going to label this number line this way, my possible points of inflection. By the way, usually textbooks, I shouldn't have done that. Usually textbooks don't refer to these as critical numbers. We use that terminology when we're talking about the first derivative. So they can call it different things. What I'm going to call them is PPI, which is possible points of inflection, instead of critical numbers. But again, the way you find these is just like critical numbers. You find out when is the second derivative undefined, when is the second derivative equal to 0. Okay, let's put those two things in the number line. I've got a half, and I've got 1. And then I'm just going to test it. And what I want to find out is on those are my cuts, and on those intervals I want to find out if my second derivative is positive or negative. If it's positive, it's concave up. If it's negative, it's concave down. So let's pick some numbers. I'm going to come over here to like a -1 and plug it in here I'm plugging it into my second derivative. That tells me concavity. If I plug in a -1 squared is 1 times 12 is 12, minus 6, minus 6, minus 6. And that came out to be 0, so I've done something wrong. Oh, hello. Sorry about this. I'm struggling a little bit this morning. If I look back up here, my possible points of inflection weren't at 1/2 and 1. It was at 1/2 and -1. I apologize. So it should be like that. So -1 didn't work because -1, it was equal to 0. It was one of my possible points of inflection. I apologize. So let's do like -2 over here. So if I plug in -2 squared is 4, times 12 is 48, minus 24, minus 6, that comes out to be a positive. I'll pick something between -1 and a half. 0 is a good one. If I plug 0 and I get 0, 0, minus 6, which is a negative. And then plug in something to the right of a half, we do 1. That'd be 12 plus 6 minus 6, which is a positive. Okay, so the question was determine the points of inflection to discuss concavity of the graph. So I would say, let's start by saying it's when it's concave up and concave down. So concave up from -infinity to -1, and then from a half to infinity. It's concave down from -1, to a half. That's when it's concave down. Okay, second part is it wants me to find the points of inflection. Be careful with this. Make sure you recognize that it says points. So finding points of inflection, the first point would be at, it changes from positive, being concave up to concave down at -1. So that's a point of inflection. Then it changes from concave down to concave up at a half. Now, if I want to find the y-coordinate, I've got to plug those numbers back into the original function. So I plug a half in the first, or -1 in the first one, I'd get 1, minus 1 is 0, minus 3 plus 1, so -2. We plug in a -1/2, and you end up with 7/16. Those are my points of inflection right there. So this should feel a lot like finding relative extrema. The only difference is we're using the second derivative, but our steps are the same. Instead of finding the first derivative, we find the second derivative, find out its critical numbers, when it's undefined, when it's equal to 0, put them on the number line, and then test the intervals. And that'll tell us concavity, and from the concavity, if it changes from concave up to concave down, then we found points of inflection. Let's try another example. Let's do number 6. So this one says, if f of x equals x squared plus 1 over x squared minus 4, and the second derivative is 10 times 3x squared plus 4 over x squared minus 4 to the third, it says list the intervals where the graph of f is concave upward, concave downward, and list the points of inflection. Okay, let's start at the very beginning, and let's find out, first of all, when the graph is undefined. So let's start up here. We know the domain. X cannot equal -2, and x cannot equal +2. Now let's look at the second derivative, right? I want to find out when is the second derivative undefined, or when is the second derivative equal to 0. Those are the two things I'm looking for. So here, the nice thing is they give us a second derivative. We don't have to find it. So when is it undefined? that's when the denominator equals 0. That's when x squared minus 4 would equal 0. So that would be at plus or minus 2. So it's undefined is undefined at x equals plus or minus 2. Okay, when is it equal to 0? That's when the top would equal 0. So if we look at the top part, 10 times 3x squared minus 4. Well, when does 3x squared minus 4 equal 0? And the answer is never. If I square something and times it by 3 and add 4, it won't ever equal 0. If you try solving that, you'd minus the 4 over and divide by 3. You get x squared equals a negative 4/3. Take the square root. It's going to end up being the square root of a negative. So that never happens. Now this is important. If I look back over here, I said x cannot equal negative 2 and 2. That means plus or minus 2 cannot be points of inflection because the graph doesn't exist there. But we're still going to put them on a number line. So I'm still going to put negative 2 there and 2 there. I'm going to slide this over a little bit since my marker is one right there. We have negative 2 and 2. I'm still going to test it, so let's pick some numbers on either side of those. So I'm going to try like negative 3. Negative 3 squared is 9, times 3 is 20. The top's going to end up being positive there. If I plug negative 3 on the bottom, negative 3 squared is 9, minus 4 is a 5, 5 cubed is a positive. So I get a positive over a positive, which is a positive up here. I'm going to plug in 0 in the middle there. The top comes out to be positive. The bottom, 0 minus 4 is a negative 4. A negative 4 cubed is a negative. Plug something to the right, which is like 3. You get a positive on top, and the bottom also comes out to be a positive in that case. So if you look at the problem, the question was, list intervals what's concave up and concave down. Okay, so it's concave up from negative infinity to negative 2. It's concave, and also from 2 to infinity. It's concave down from negative 2 to 2. Now this is important. It's asking, the last question is, find the list of points of inflection. There are no points of inflection. The only possible ones would be at negative 2 and 2, because it does change from concave up to concave down. But, right, the graph does not exist there. Those numbers are not included in your domain. So there are no points of inflection. Okay, so second derivative number line test, that is for finding concavity and points of inflection. You do exactly the same steps as you do with the first derivative, you just do it with the second derivative. But other than that, hopefully we can make that connection and we're following the same procedures, the same steps. There's a second part to this lesson. I'm going to do it as a separate video, so I'm going to stop this here. Then I'll make a second video that talks about the second derivative test for relative extrema for finding mins and maxes.